We are going to be doing a couple more questions on geometry, just to make sure that we're on the right track. And then we're going to be moving on to tangents and how they link to radii and theorems relating to that. Because there is quite a lot to learn in the geometry chapter for IG. And I feel that the best way to do this is literally by doing example and example and example and seeing different methods of doing it. Because people think very differently. And the best way you can learn is actually by learning as many possible ways of doing something as you can. All right. So let us draw up our diagram. So there's a smaller circle, and then we have a bigger circle, and it looks like we need it to be kind of like that-ish. All right. And then we have some lines, and the lines go from here to there, from there to there. We then also have a line from here to there, and one from there straight through it to the other side, and from there joining. That looks like a nice diagram. All right, and then we are told as well that that is point O. And this is O1. We then have P, P1, and P2. We then have Q up at the top. We have N over there. We have M over here. This is N1 and 2. And then this is Y. All right. You are told that O is the center of the larger circle. Luckily, it's quite clear to see which one is the larger circle. And then you're also told that it lies on the circumference of your smaller circle. You are asked to show that MP equals NP. So just to change colors, you are asked to show that this side length equals this side length. Hi. All right. So question comes about, where could we find this in the textbook? So in the textbook, it is, let me quickly find it for you. All right, so we found that it was lesson 96 and 97, and therefore you can go to check that in the book. So we are now looking to solve this. How can we show that these two sides are equal? Well, most of the time when you're asked to do this, it relates to isosceles triangles. Because remember, in an isosceles triangle, you have two sides that are equal and also the two base angles that are equal. So if these two sides are indeed equal, that will mean that this angle here and this whole thing over here, N1 plus N2, must be equal, because that's your isosceles triangle. So how can we do this? Well, you've been given that this is Y. Cool. We need to see, can we prove that N1 plus N2 equals Y? And if we can, we've proven it's an isosceles triangle. And if it's an isosceles triangle, we know that MP equals NP. So if this is Y, we can go to O1. We can see that O1 is actually 2Y, because we have a line that goes there and it subtends an angle, but also it's subtending an angle at M, which means that you can use your angle at center as 2 times angle at circumference. Angle at center is 2 times angle at circumference. So therefore, this is 2y. Now, if we have a look in our smaller circle, we see that this angle here is subtended, but the exact same points, N and Q, have also subtended an angle there at P1. All right. So just so that it's slightly clearer, I'm going to get rid of these. All right, so it's actually at P1. So we know that P1 also will equal 2y, and that's because of angles in the same segment. So this arc, or essentially chord, subtends an angle there at the circumference and there at the circumference, and therefore they are equal. All right, so therefore those two are equal. But now this P1 angle, this is quite an interesting special angle. This is actually the exterior angle of the triangle I'm looking at, NPM. So that means, in essence, and I'm going to do it up here for space purposes, that P1 equals M plus N1 plus N2. And that is the exterior angle of my triangle. But I know what this is, and I know what this is, and I'm actually trying to find what this whole thing is. I know P1 is 2y. I know M is y. Which means that N1 plus N2 must equal, after taking the y over, just y. So if that equals y, and that equals y, those must be base angles of an isosceles triangle because they are equal. And therefore, MP equals NP because we are dealing with sides opposite equal angles. Quite interesting, I think. So let's do another one. Here are my circles. There's a nice big circle. Now I'm going to have some lines. So line down. And there's a line that goes across. From here, there's a line that crosses up. And then there's one that joins there. All right. And we have L, 1 and 2. We have A. We have E that is given as a right angle. We have P1 and 2. And then we have point M. You are given that, should that be P2 or P1? So P1. So P1 equals X. So let's change color. So that means that this one over there, that equals X. And I am asking of you to find L2 in terms of x. So it's very important as well to know what this phrasing means, in terms of x or y or whatever. Because that means that you are actually going to be getting an expression with only x and numbers. So there's not going to be some other like angle A plus 2x or something like that. It literally needs to be just an x and some numbers. It might be like a 45 minus x, or it could be a 180 plus x, or 180 plus 2x, or something like that. It could be more than one term, but it's only meant to have an x and numbers. So x is your only unknown. All right, how are we going to get to L2? Well, if we know this angle, we also know that that is 90 degrees. We can find the value of m over here. So I know that E is 90 degrees, and that was given to me. So therefore, I know that E plus P1 plus M is 180 degrees because of angles in a triangle. This is 90, this is x, and this is what I'm trying to solve for. So therefore, M is actually 90 minus x. All right. Now, with this being 90 minus x, because of angles in the same segment being the ends of a bow tie, because it kind of does look like a bow tie, because this is always going to be the shape when dealing with angles in the same segment. So it looks like one of those like cartoon bow ties, where it's like sharp corners and they kind of cross over each other. So there's your bow tie, and the corners of your bow tie will always be equal. And those corners will be equal because of angles in the same segment. So I know that L1 equals 90 minus x, angles in same segment. And then this is the one that I'm trying to solve for. Now, since I know what L1 is, it's going to be far easier because I know that L2 is 180 minus the 90 minus x. And the reason for that is adjacent angles on a straight line. So 180 minus 90 gives me 90, and minus x gives me plus x. And that is my answer for L2 in terms of x. All right. There is another way of doing this as well, and you can use exterior angle of a triangle and stuff like that. I'm going to give 1 minute for people to just finish copying this, and then we can have a look at that. All right, so let's clear this up. So what if we didn't know this stuff? Let's go back. All right. This stuff. All right, fine. You want to be like that? Fine, be that way. All right. Do they give the bow tie rule in the textbook? I believe they do. I don't know if they're as explicit, but it is angles in the same segment, so look for that. But I know that they do explain it. They don't really focus and be like, hey, look at this. But it is there. I think it's kind of just given as like a side result, which is quite sad. All right, so the other way that you could have done this if you wanted to, you could have seen angles in the same segment immediately here already. So we know that that side is x. So we know that angle A is x, angles in same segment. I know that this angle over there is 90 because it was given as perpendicular. And therefore, I know that L2 is A plus E because of the exterior angle of a triangle, which means that it is 90 plus x. Far simpler it looks like, but either you see it or you don't. Because remember, exterior angle of a triangle, this is an exterior angle because your side was extended, and the exterior angle of a triangle equals the interior opposite two angles added together. So it is the sum of the opposite two interior angles.